Now that we've learned about network models, layers, and addressing, let's move on to the next topic, Ethernet LANs. In this section, we'll delve into basic Ethernet operations, as well as cover repeater, hub, and bridge operation, and Ethernet switch operation. Today's complex networks are built using many different network devices. The names of these devices might be familiar to you and include routers, switches, and more. But to understand what these devices do and how they work, we first need to take a look back in time. Networks have grown at a pace not anticipated even a few years ago. Worldwide, nearly 1 billion PCs were in use by the end of 2006. New network devices have been developed along the way to address specific problems resulting from this growth. To understand the different network devices used in today's networks, it's helpful to understand the predecessors to those devices. To gain that understanding, we're going to take a look at the history of a fictional company, call it Acme Company, from its roots in someone's garage to that of a multinational company. When Acme Company was established in the mid-1980s, the company had only a few PCs. Their networking needs were pretty simple. They needed to share documents and spreadsheets as well as a single printer. In networking terms, PCs and printers are known as end-user devices, hosts, or just devices. As we mentioned in Section 1, a geographically limited network is called a local area network, or LAN. To create a LAN, end-user devices must be connected, either physically with cables or wirelessly. A LAN also requires a set of rules controlling communication on that connection. And the most common set of rules is called Ethernet, a LAN network technology developed in the 1970s. Ethernet is a set of standards that define rules, such as frame format, as well as how computers communicate with each other over a single wire shared by all devices on the network. These rules give any new device attached to the wire the ability to communicate with any other attached device. Although Ethernet technology has evolved considerably since it was first implemented, the fundamental operations remain the same. Ethernet standards include a number of components. First, there are the physical layer characteristics. In other words, what does the physical layer, or layer 1, consist of? Next, there is the protocol that controls access to the network. And finally, there is the frame format. We'll cover all of these components. Ethernet was originally deployed with multiple computers connected to the same physical wire or cable. This physical network topology, or layout, is called a shared bus, meaning that when one computer transmits data, all other devices on the shared bus or network segment receive it. If there is a break in the cable, devices can no longer communicate. By the way, the term network segment means different things to different people. In this course, the term network segment, or simply segment, refers to the group of network devices that compete with each other for access to the wire. To refer to the actual cable or wire used to connect network devices together, this online program will use the term physical cable segment. An introduction to how networks work. Let's look at the functionality of network segments in more detail, and how do end-user devices connect to the network segment. Email messages traverse the millions of miles of networks worldwide connect to the same network to the correct computer. How do devices know when it is their turn to send exercises to help communicate and reinforce the information? Receive the data. This program is about 5 hours long. The data is intended for that device. We'll answer all 3 of these questions in this section. When you think about it, to connect to the network segment, you type a device uses a network interface mouse clicks, or an email is sent nearly instantaneously. Click the link on screen if you would like to learn more about NICs. You launch a web browser, continue button, and type a URL with this topic, and a web page automatically appears. How does that happen? Today, networks impact all of us, from corporate workers collaborating on projects to grandparents exchanging photos with their grandchildren. But how many of us know how that email or photo gets from point A to point B? Or how a simple URL gets to the correct web server? At its core, a network is simply the conduit one computer uses to send information to another computer. Add up all those conduits, though, and soon you begin to wonder how those millions of networks, all interconnected to form the internet, manage to keep all that data straight. And considering there are billions of computers on the internet, how is it possible that data manages to end up in the right place at all? In this program, we answer all these questions. We'll start with a generic model of how networks operate. specifically networks like the Internet, then discuss specific networking technologies and protocols. At the end, we combine this information and show you just how data gets from point A to point B. So let's get started. We just mentioned that a network is simply a conduit that connects at least two computers. In fact, the two devices don't need to be computers. A computer sending data to a shared printer is using a network. Ethernet operates at layers 1 and 2,
are more complicated than
which
that.
You might remember are
Every
the physical
business
layer
with more than
and
a
the data
handful
link
of
layer.
employees
has at least one
Both
network.
of these layers are
which is what
implemented
allows
on
you
the
to
NIC.
share a spreadsheet or
The
document with a
Ethernet
coworker.
physical layer defines
Large
such
companies
things
commonly
as
have
the
remote
connection
offices
speed
connected
and the
to
type of
corporate
cabling.
headquarters. Both have
Many
evolved
homes
over
are
time
networked
and are
too,
discussed
so
later
your
in this
entire
section.
family can all share a single printer instead
The
of buying
second
printers for
component we
each
mentioned
computer.
previously was the protocol
Finally,
controlling
more
access
people are
to
using
the
mobile
network or
devices
wire.
to access
That
email
is,
and the
how
Internet.
do devices
And
know
while the
when it is
details of
their
each
turn to
specific
send
type of
data?
network are beyond the scope
Access
of
to
this
the physical
course,
wire or
all
segment
networks,
is controlled
however
by a
simple or
media
complicated,
access control
use the
or
same
MAC
fundamental
protocol.
concepts and building blocks.
Ethernet in particular
There are two
uses
basic
carrier
kinds of
sense
networks.
multiple access
Any
with
group
collision
of computers
detection,
on a single
or
geographically limited network
CSMACD,
is called a
as its
local
MAC
area
protocol.
network or LAN.
Other MAC protocols
LANs allow
exist
users
for other
to exchange
technologies.
documents and share resources
To understand
such as printers or
CSMACD
file servers.
operation, think of a
A
group
LAN
of people
can be
having
either
a
wired
conversation.
or wireless,
As
or
we
a combination
discussed in
of both.
Section 1 on protocols,
We discussed the
in
different
general,
LAN components
human
and how
conversations
information
work
is
only
sent
when
from
one
one
person
computer
talks
to
at a
another
time.
later in this course.
That way, everyone in the group
LANs can be
hear and
connected to
understand
other
what is
LANs
being
by
said.
way of a wide area network.
The same
or
is
WAN.
true of computer networks.
A WAN might
And
connect
in
a
the case
remote
of
sales
Ethernet
office
LANs,
to corporate
the
headquarters across the
CSMACD
country
protocol
or across the
regulates
world.
the conversation.
A WAN might also
If a
connect your
device
home
has
network
data
to
to
the
transmit,
Internet.
it
We
listens on the
discussed
wire
several
to see
different
if
WAN
any other
technologies
device is
and
transmitting.
the network components
If
used
the
to
wire is
interconnect
idle,
LANs
the
later in
device
this
sends
course.
the data.
But before
All
we can
other
start
devices
discussing
on
the
this segment
details
receive
about
the
the different
transmission.
network components used
Now,
in
what's
LANs
important to
or
remember
WANs,
about the CSMACD
we need to understand how
protocol
information
is that it
created by
allows
an
a network
application on
device
one
to either
computer
transmit data
gets to
or
an
receive
application
data,
on another
but
computer.
not do both
We'll start by
simultaneously.
examining a similar
This
network
type of
model
system
in the
is
next
known
section.
as half-duplex communication. A half-duplex system provides for
Think about the
communication
last time
in
you
both
mailed a
directions,
letter.
but only
How
one
does the
direction
post
at a
office
time.
actually route the letter to its
Half-duplex data
destination?
transmission is similar to
In
using
many
a
ways,
walkie-talkie.
computer networks work
If
on
you
the
want
same
to talk, you need
principles
to
as the
press
post
the
office.
talk or transmit
Let's
button.
look at this in more detail.
While you're talking, the other person
Imagine
cannot
you've written your
transmit
friend
to
a
you.
letter. You put it in an
Full-duplex
envelope and
communication,
address
on
the
the other
envelope.
hand, sends and
If you
receives
examine
data
the
at the
address
same time.
closely, you'll
We
notice it is
discuss
written in a
full-duplex
hierarchical
communication in
format,
more detail
starting
later
with the
in
most
this
specific
section.
information, your friend's name,
On a
followed
network
by the
using
street
half-duplex
address,
communication,
and ending with the
when
postal
one device
code,
on a network
which is the most
segment
general
transmitting
information.
data, other
The
devices
post office
cannot
needs
transmit
each
data.
different level or layer
Any
of
device that
information
needs to send
route
data
the letter
must
to its
wait
final
until the line is
destination.
clear.
Once you address the letter,
While all
you drop
computers
the
listen to
envelope
the
in a
wire
post office
first
box,
to make
and
sure
the
the
mail
wire is
carrier
idle
picks up the
before
letter
they send
and
data.
takes it to the nearest post
Sometimes
office.
data collisions do
All this
occur.
may seem very obvious, and
Let's
really
return
it's
to our
analogous to the
conversation
steps
analogy to
involved
see
in
how this
writing and
problem
sending
can
an
happen.
email. Clicking the
If there is
send
a lull
button
in the
is the
conversation
equivalent of
and two
dropping it
people
in the
try to
mailbox.
say something at the same
It's
time,
at the post office,
others in the
though,
group might not
the
understand
entrance
what
to the
either
network
person
in this
is saying.
analogy, where we're going to
At this
focus our
point,
attention.
one person stops for a moment
The
and
post
allows
office
the
sorts
other
the
person to
envelopes by
resume speaking.
destination using the postal code, the most general
The
information
same
in
thing
the
can
address.
happen if two devices
Your
listen
letter
to the
is
wire,
placed into a container
believe it is idle,
and sent to the
try
next
to
post
transmit
office
data
along
at
the
the same
route to its
time.
destination.
This
where the letter
condition
is put
is
into
known as
another
a collision,
container, and the
and this
process
is
is
where collision
repeated until it
detection,
reaches the
the
final post
CD
office.
part of
Notice that the
CSMACD,
envelope
comes
might
into
be
play.
placed into several different
When a
containers
collision
along the way.
occurs,
But
both
the
transmitting
address on the
devices
envelope
stop
is never
transmitting,
changed.
wait a random amount of time,
Another key
and
point
attempt
is
to
that the first
transmit
post
again
office
when the
doesn't
wire is
usually
idle.
use the entire postal code.
Click the link
just
on
the first
screen
few
to learn
digits.
more about how
As
collision
the envelope
detection
makes
works,
its way from post
or
office to
click
post
the
office
continue
toward the
button
final
to continue with
destination.
this topic.
The sorting equipment looks at additional digits. Eventually, the entire postal code is used, and all the mail in the container has the same postal code and is destined for the same post office. Once there, it's then sorted again based on more specific information, the street address, for the mail carrier to deliver. Only when the envelope is delivered to the correct house is the recipient's name examined, because more than one person might reside at that same address. Computer networks work in much the same way. We'll cover this topic in more detail later. But in short, like handing off letters and packages from post office to post office, networks forward packets of data from one device to another until, like the final post office, the final device forwards the data to the destination computer. To understand networking, it helps to start thinking in layers. In fact, a model was developed many years ago to break up the complex process of sending data from one computer to another into 7 steps or layers. Called the Open Systems Interconnection, or OSI, reference model, this model identifies the steps and functions that must be completed at each layer when computers communicate over a network. These 7 layers are like a set of building blocks stacked on top of each other. In fact, the 7 layers combined are often referred to as a network stack. The OSI model, however, provides only guidelines on how computers communicate over a network. It does not provide detailed procedures on how to actually make this communication happen. These procedures for communication are called protocols and define how actual communication occurs. A protocol is a formal set of written rules or procedures that computers must understand, accept, and use to be able to talk to each other over a network. Different protocols are used at different layers of the reference model. Just as 2 people need to speak the same language to communicate,
is also known as a
collision
collision
domain
domain.
The same protocol
With
at the same layer for
CSMACD,
the data to be
as
communicated.
more devices are added to the network segment or
More than
collision
merely
domain,
a common language,
more collisions
protocols
occur,
are like the rules of
degrading
etiquette
overall
frequently
network
encountered
performance.
among spoken
The
languages.
increasing frequency
When you
of
start a
collisions was
conversation,
a major
you
obstacle
usually say
in the
hello
development
and
of
wait
networks.
for the other person to greet you.
We'll see shortly
You
how
typically
network
take
designers
turns talking
overcame this
and asking
obstacle.
questions. Network protocols operate in the same
Now let's
manner,
move on to the third
defining
question
rules
posed
such
earlier.
as when computers
How
are
do
able to
devices
transmit
know
data,
which data is
which
intended for
computer
them?
the data is destined for,
Let's
and
begin
what
by
to do
looking
if
at
the
how
data is
data
not
is
received.
encapsulated. When a device needs to send data,
The
the
OSI
NIC
reference model
encapsulates
also
it into an
describes how data
Ethernet
should be
frame.
passed from one layer to
Ethernet
the next.
standards define the
On
layer 2
sending
frame
computer,
format,
data flows
which has
down
evolved
the
over
model or
time.
stack.
You
At
might
each
hear
layer
people
in the
use
stack,
the terms
protocols
Ethernet
add
and
headers and trailers or
802.3
footers,
together
which
or
contain
separately.
information such as
Click
addressing
the link on
and error
screen to learn
control
more about
information.
Ethernet evolution
When a lower layer
and the term
receives information from an
802.3,
upper layer,
or
it
click the
considers
continue
entire
button to
package's
continue
data
with this topic.
and adds its own header and, if needed, footer or trailer to the data. The process of adding headers and footers to data layer by layer is called encapsulation. On the receiving computer, data flows up the stack. At each layer, the addressing or protocol information is examined and removed layer by layer until the computer gets to the actual data. The process of removing headers at each layer of the stack is called de-encapsulation.
The Ethernet frame
The
includes
OSI
the
reference
destination
model is
layer 2
theoretical in
address
nature
of the
and,
device
as we
receiving the
mentioned
data,
earlier, does not
as
define
well as a
actual
source layer
protocols.
2 address of the
The
device
Department of
sending the
Defense
data.
and the Internet Engineering
Each
Task
NIC has a
Force
unique
developed
layer
a
2
simpler
address that
four-layer
is
model
assigned by its
called
manufacturer.
the TCP/IP reference
The
model.
manufacturer burns
model
this
defines
address
specific
into a
protocols at
programmable
each of the four
read-only
layers,
memory or
such as
PROM chip
TCP
on the NIC.
and IP.
The
Two of the
NIC
Internet's
uses
core
this
protocols.
address as the source address
A group
in
of
a
network
frame.
protocols that work together
For the
is called
destination
a protocol
address,
suite
it uses
or
the
a
address
protocol
that is
stack.
burned into the NIC
So
on
the
the
protocol
receiving
suite
device.
that governs internet
A
communication
layer 2 address is
commonly
also
called
known
the
as a hardware
TCP/IP
address,
protocol
a physical
suite,
address,
and is
or a
based
MAC
on the
address.
TCP/IP
In
reference
this course,
model.
we will use the
The
term
name is a
MAC
bit misleading
address for a
because
layer
TCP
2
and
address.
IP are only two of dozens
Use
of
your
protocols
mouse to
that
learn
make up the
about the
suite.
other fields in the Ethernet frame.
Let's take a moment to compare the two
Click the
reference
continue
models.
button when you are ready
On
to
screen,
move on.
you'll see both side by side. The first difference you'll notice is that the first 3 layers of the OSI reference model fold into a single layer in the TCP/IP reference model, simply
The
called
destination
application layer.
address is the layer.
The transport
The
and
source
network layers
address is
map
the layer
directly
2 or
between
MAC.
the two models.
The type
The
field
TCP/IP
identified
reference model
the
merges
data
the
field
lower 2
contains the
layers
original
into the network
The
access
checksum
layer,
field
which
includes-
focuses on how data is transmitted
Let's
over
take a
any
closer
type of
look at
physical
MAC
network,
addresses,
regardless
and
of
how
whether
they're
it's
used
a
by a
LAN
device.
or a WAN.
A
The
MAC address is a
TCP/IP model
48-bit
is not
or
concerned
6-byte
with the
address
details of
that
this layer
uniquely
and
identifies
uses
a device's
existing
NIC.
standards, such as Ethernet
We'll cover bits
or
and
ATN.
bytes in detail
We
in
cover
section
these
4.
technologies later
But
in the
for
course.
now, understand that a byte is
In
comprised
practice,
of
however,
8 bits
many
of data.
people discuss
So 6 bytes
TCP/IP-based
is the
networks
same as
using
48
a 5-layer
bits.
model that is a
Take a look
combination
at
of
the
the
MAC
4-layer
address on screen.
TCP/IP model
MAC
and
addresses
the
are
7-layer
typically
OSI
expressed
model.
in hexadecimal
This commonly
format,
used
a
networking
numbering
model
system that
uses
uses
the
0
first
through
4
9,
layers of
but
the
then
OSI
also
reference
represents
model.
numbers greater than
You'll
9
notice that
using
where
the
the
letters A through
TCP/IP
F.
model combined
We'll
the
discuss
original
this and
OSI
other
data
numbering
link
systems
layer
in section
and
4.
the physical layer into a single
Each
layer
digit
called the
represents
network
4
access
bits.
layer.
So one
This
byte,
model breaks them
which
back
is 8
out.
bits, is
At the
represented
same
by
time,
2
like
digits.
the TCP/IP model.
For example,
this
in
model
this MAC
collapses
address,
the OSI
00
model's
is the
application,
first byte,
presentation,
90
and session
is the
layers
second byte,
into one
and
layer,
69 is the
referred
third
to
byte.
as the application
The
layer.
bytes in MAC addresses
Although
are
there are
displayed
only
using
5
dashes,
layers in this
colons,
model,
or dotted
the
decimal
layers are
format as
commonly
shown on
referred
screen.
to using the original
Breaking
OSI
down MAC
numbering
addresses
scheme.
further,
Layers
each
1
is
through
broken
4
down
are the
into
lower
2
layers,
components.
and layer 7
The first
is
3
the
bytes of the
application
MAC
layer.
address comprise the
course uses this
organizationally
commonly
unique
used
identifier,
hybrid
or
networking model.
OUI,
We
that
cover
every
each of its
Ethernet
layers
equipment
in more detail
manufacturer
in a
is
moment.
assigned by the Institute of Electrical and Electronics Engineers, or
Now let's take a
IEEE.
closer look at
In
how
our
data is
example,
sent from one
we've
computer to
used
another.
00,
We'll use the 5-layer
90,
network reference model as a
69.
guide. and will
which is
also
the
employ
Juniper
the
Networks
post office model
OUI.
we discussed earlier to
The
illustrate some
manufacturer
concepts.
then uses the remaining
As you
3
saw
bytes
already,
to assign a
at
unique
each layer
number
of the
to the
network
NIC.
reference model,
When the NIC
specific
is ready to
information
send
is added
data,
about what
it
type
adds
of
the
data you are
destination
sending
and source
and
MAC
where it's
addresses
going.
into the frame
Ultimately,
and
your data is
transmits it
converted
on
to
the
electrical
segment.
signals,
To keep our
transported
animation
over the
simple
network,
right now,
and then
we'll just show
processed
the
by the receiving
destination
computer.
address on the frame,
Now let's examine what
designated with the
specifically
letters
happens in each
DA.
layer, including
Because
which protocols
Ethernet
are
is a
used.
shared medium, every device on the segment receives every frame and
When you
compares the
send an
frame's
email,
destination
the email
MAC address
program on your
with its
computer,
own MAC address.
such as Microsoft Outlook,
If the
interacts with
destination
the
MAC address
application
does
layer.
not match,
Behind
the
the
NIC
scenes,
discards
the
the
email
frame.
program sends the
If
message
the
or
destination
data
MAC
to your
address
internet
matches,
email server
the
for
NIC
delivery.
processes the frame.
The email application uses
First,
the
the NIC compares the
SMTP,
cyclic
or Simple
redundancy
Mail
check, or
Transfer
CRC
Protocol
checksum
application layer
on the frame
protocol for this
received
communication.
with the CRC that was
Application layer
generated by the
protocols
sending
usually
computer.
specify how
Next,
data should
if
be
the frame
encoded,
length is the
compressed, or
same
encrypted,
and the CRCs
and
match,
how sessions
the
should be
NIC
managed.
examines the frame type to determine the
Some
upper layer
application
protocol.
layer protocols are shown
Then
on screen.
it strips off the Ethernet
Click
frame
any of the
and
links
forwards
on
the
screen
data
to
to the
learn more
appropriate
about
upper
each
layer
protocol. Or click the
Before we
continue
close
button
out the
to
subject
continue
of
with
MAC
this topic.
addresses, there's one more detail we need to cover. So far, we've been talking about MAC addresses that are unique to both the sending and destination devices. That is, when one device sends data to another device, the destination MAC address is a unique MAC address, which is also known as an individual or unicast address. But what if one
Using our
device is
postal
sending
mail
data
analogy,
to multiple
our
devices?
data at this point is like a
This
letter,
scenario
written in
requires
a
MAC
language the
addresses as
recipient
well,
understands and
but of a
following
different
common
sort.
conventions for letter
If a
writing.
device needs to
However,
send the same
our
data
does
to every
not yet
device
have
on the
an
network,
envelope
it
specifying where
uses
it
a
should be
broadcast
sent.
destination MAC address.
The application layer
This
sends the
special
data
address
down the
used for
stack to the
broadcasting
transport
is shown on
layer.
screen.
The transport
If
layer
a device
specifies
needs to
which
send the
application
same
layer
data to a
protocol
group of
should be
devices
used
on
to
the same
process the
network,
data
it
once
must
it
use
arrives
a
on the
group
receiving
address
computer.
or multicast MAC
Each
address.
application layer protocol is
Multicast
assigned a unique
addresses
numerical
always have the
identifier
first bit
called a
of the
port.
first byte set
Note
to
that
1.
this port is a software
Unicast,
port,
broadcast,
not a
and
hardware port.
multicast addresses
For example,
are all hexadecimal
HTTP
addresses.
uses port 80, DNS uses port 53, and SMTP uses
Let's
port
return
25.
to the history of the Acme Company.
This destination
The company
port number
grew
is
at a rapid
analogous to the
pace,
recipient's
and needing
name
more
on our
space,
envelope.
expanded into
Just
nearby
like there might be
buildings.
multiple people living at a
Ethernet
single
has strict
address,
rules
each
about
with
the
unique
length
name,
of a physical cable
multiple
segment,
programs
as
might
well
be
as the
running on
number
the
of
destination
devices on the
computer
cable.
using different
So to
application layer
accommodate this
protocols.
growth and add more
Each
computers and
application layer
printers to the
protocol
network,
has a unique
Acme
port
Company
number,
used a
so
network
incoming
device
data
called
can
a
ultimately
repeater
find the
to
correct
extend
program.
the length of its
The
Ethernet
transport
physical
layer
cable
includes
segment.
the destination
A
port number in
repeater
the
is
header
a physical
it adds
layer
to the
device
data.
used to connect
When
two
the data
or more
arrives at the
separate
destination
physical
computer,
cable
the
segments
transport layer
together,
there examines
making it
this
act
number
like one
to
long
determine the
cable.
application layer
A
protocol
repeater
the data
is a
should be
simple
sent
hardware
to.
device that regenerates electrical signals,
The transport layer
sending
on the
all
sending
frames
computer
from one
also
physical
includes
cable
a source
segment to
port number
another.
in the header, which is
Click
similar
link
to the
on
name
screen
in the
if you
return
would like
address.
to learn more about rules
The
governing
source
the
port
length
number,
of physical
typically
cable
a random
segments,
number,
and the number of
uniquely
repeaters
identifies
that
the
can be
connection
deployed
on the
on a
sending
single
side.
LAN. Or
This
click the
port
continue
allows the
button to
receiving
continue with
computer
this
to
topic.
carry on multiple sessions with the sending computer without intermixing the data. Beyond identifying the destination and source port numbers, the transport layer has a second important responsibility as well. Again, let's consider our letter. When you are ready to mail your letter, you have a choice to make. You can simply add a stamp, drop it in the mailbox, and assume it gets there. Or you can request a return receipt, which the post office returns to you upon delivery, so you can be assured it has arrived. As its second responsibility, the transport layer offers a similar choice for reliability. The User Datagram Protocol, or UDP, and the Transmission Control Protocol, or TCP, are two transport layer protocols in the TCP/IP protocol suite. UDP and TCP are also known as Layer 4 protocols because they take place in the fourth layer, the transport layer. UDP is a very simple and fast protocol. UDP is a best effort delivery service providing no delivery notification, error checking, or recovery procedures. It's exactly like dropping your envelope in a mailbox and
Ethernet
hoping for
networks
the
were
best.
originally implemented with
With
coaxial
UDP,
cabling.
the sending computer doesn't
With the introduction
know if the receiving
of the
computer
IEEE
actually received the
10-based
data.
T standard in the late 1980s.
Applications sending short
Ethernet
messages
networks
or
started
time-sensitive
using twisted
data,
pair
such as
cabling.
DNS, online
Click
gaming,
the link on
voice
screen
over
if you would like to
IP,
learn more
or
about the
VoIP,
10-based T
and
standard.
streaming video
Or
applications
click the continue
like
button to continue with
IPTV
this topic.
often use UDP because speed is critical. Voice and video applications are designed to handle occasional packet loss without a major impact on performance. For example, you might see a video jump, or you might miss a word in a phone call. Sometimes you might not even notice a problem. When you type a URL in your web browser, behind the scenes, you are using DNS to find the IP address of the web server. DNS must operate quickly, and most of the time you receive a quick DNS
Twisted pair
response.
cabling consists of
But if for
twisted
some
pairs
reason
of
you don't
unshielded
receive a
but
DNS
insulated
response,
wires,
no harm done.
It is also
you can
known
simply
as
try to access
unshielded
the web
twisted
server
pair
again later.
or UTP cabling.
TCP, on the other
first
hand,
10 base
is a
T
more
networks
robust
used
protocol,
ordinary
providing
telephone
delivery
cabling,
notification,
which is a type of
error
twisted pair
checking,
cabling.
and recovery procedures.
In this type of cable,
with
there
TCP,
are 4 twisted
the
pairs
receiving
of wires,
computer tells the
2 for
sending
transmitting
computer
data
when the data
and
was
another 2
received.
for receiving data.
It's equivalent to sending our letter by registered
At this
mail
time,
with a
a
return
new device
receipt.
called a hub also became
HTTP,
available.
SMTP,
Acme replaced
and
their
FTP
repeaters with
all
hubs.
use TCP.
Now, the physical topology
TCP
or
accepts
layout
data
of their
from the
network
application
changed
layer
from a shared
protocol
bus
and
to a
cuts the
star
data into
configuration.
smaller pieces called
In
segments
Acme's old
to
shared
ensure a
bus
steady flow of data between
many
two
devices were
computers
daisy-chained
regardless
together
of the
using a
differences
single
in connection
network
bandwidth.
cable, which meant that if the
Segmentation
cable failed
is like taking
or
our
if one
letter
device
and
on the
sending
cable was
each page
causing
in a
network
separate
trouble,
envelope.
every device on the cable
By
could be
numbering the
impacted.
pages, the recipient can
In a
place
star
the pages back
configuration,
in order.
each device uses
Likewise,
its own twisted pair
TCP
cable to
assigns a
connect to a
sequence number
port on the
to
hub.
each segment.
If a cable
On the
fails,
receiving
it will
side,
impact only
TCP
one device.
uses the sequence
And if
numbers
one
to
device
put the
is causing
segments
trouble
back
on the
together
network,
in the correct
that
order.
individual device can
The
easily
receiving
be
side
unplugged.
uses the sequence numbers
Like a
to
repeater,
tell the sending
a hub
side
simply takes
when
a signal
segments have
that
been
it receives
received.
from one connected
Just
device
like the return receipt
and
in our
passes it
postal
along
analogy.
or repeats it to
If
all
the sending
other
side
connected
does not
devices.
receive an acknowledgement within a
A
reasonable
hub is
amount
not
of time,
an intelligent
it
network
resends
device.
the segments.
It does not look at the MAC
Once
addresses
this process is
or
complete,
data in the
the
Ethernet
transport
frame
layer sends
and
the
does
data
not
or
perform
segments
any type
down
of
to the
filtering
network
or routing
layer,
of the data.
which is also known
It is
as layer
simply
3.
a junction that joins
The network
all
layer
the different
takes a
devices
segment
together.
and adds a header to create a packet.
Even though each
The
device
layer
has its
3
own
header
cable
contains
connecting
a
it to the hub,
destination and
access
source
to the
internet
network still
protocol
operates
or
by
IP address.
JNCIA-SEC,
You'll
and
also
collisions
hear
can
these
occur on the
addresses
shared
referred
bus
to as
inside
layer
the
3
hub.
addresses or logical
Having twisted
addresses.
pair cabling and
Layer
hubs
3 addressing
simplified
can be
many
compared to
networking
adding your
operations
recipient's
for
address
Acme.
and your return
But as more
address
time
on an
passed
envelope.
and Acme's network
We cover
continued to
IP
grow,
addressing
network
in much
performance
greater
still
detail
suffered,
later in
and
the
employees
course.
complained.
Notice
Remember
that
our
the network
discussion of
layer
the rules
treats the
governing
data
a
it
group
receives
conversation?
from the transport layer
As more and more
as
people
one
join the
piece of
group,
data.
it becomes
It
more
does
and more
not need
difficult
to
to have an
inspect the transport layer
uninterrupted
headers
conversation
or the original
understand what
data
everyone
during
is
the
saying.
encapsulation process.
One way to fix this problem
As
is to
part
break
of
the
its
large
own
group
headers,
up into
the
several
network
smaller
layer
groups,
adds a
which is
number
how networks
identifying
handle
the
the
upper
same
layer
problem.
transport layer protocol.
Let's see how Acme
Each
divided
transport
up their
layer
network.
protocol is assigned a unique
The group of
identifier.
Ethernet devices that compete with each other for access, you might remember, is called a collision domain or network segment. A hub operates at layer 1 and makes both sides of the hub act like one very long physical cable, repeating each and every frame. As more and more computers are added to the network, more potential for collisions is created. To break their network up into smaller segments, Acme installed a network device called a bridge. Just like a repeater or a hub, a bridge connects 2 or more physical cable segments to create one larger network. Unlike a repeater or a hub, though, each side of the bridge becomes a separate collision domain or network segment. So a bridge can be used to break up a large network into separate collision domains. This process is often referred to as network segmentation. By breaking the large networks into smaller collision domains, the number of devices competing for network access declines, and of course the number of collisions also declines. If a collision does occur, the bridge isolates the collision to a single domain. A bridge operates at layer 2 and helps regulate traffic flow using MAC addresses. Let's see how this process works. On screen is a bridge with 3 ports. Each port is attached to a hub, and each hub is connected to 2 devices. The MAC address of each device is shown next to the device. Ethernet bridges have 3 basic functions: forwarding frames, learning MAC addresses, and controlling traffic. A bridge uses a MAC address table, which is like a database, to help control and limit traffic on a network. Because a bridge is a layer 2 device, it can examine the source MAC address of each received frame. A bridge can then record the source MAC address and the port on which it was received in its MAC address table. Let's see how MAC address tables are built and how they are used to improve overall network performance. When a bridge first powers on, the MAC address table is typically empty. When an end-user device sends out a frame, the bridge receives it and looks at the source MAC address. In the on-screen animation, the source address is now designated on the frame with the letters SA. If this MAC address is not in the MAC address table, the bridge adds it and associates it with the port on which it came in. Next, the bridge examines the destination MAC address. If the destination MAC address is not in its table, the bridge forwards the frame out all of its other ports. This action is also known as flooding. Because the bridge builds a table of addresses when they come in, the bridge eventually learns through which of its port's destination devices are located, so it doesn't have to flood each and every frame out all its ports. When the bridge receives a frame with a destination MAC address in its MAC address table, it can forward or drop it selectively, reducing overall network traffic. If the destination MAC address is in the MAC address table and resides on the same port where the frame arrived, the bridge simply drops the frame because the end user device has already received it. It does not forward the frame to the other ports or segments, reducing overall network traffic. If the destination MAC address is in the MAC address table and is located off a different port, the bridge forwards the frame only on that port, again reducing overall network traffic. If the destination MAC address is a broadcast or multicast address, the bridge must always forward it out every other port. Because a bridge is just another device in the collision domain, it follows the same MAC protocol as every other device. It is important to note that bridges never change the destination or source MAC address. They simply look at the destination MAC address to make their decisions. Here's a chance to see how well you understand bridge functionality. The bridge has just received the frame shown on screen on port 2. What will it do now? Type into the MAC address table to make any necessary additions. Then select each action that the bridge will take. When you are finished, click Check Answer. Bridges were huge advances in the development of Ethernet LANs, but they weren't perfect. Often bridge network segments were interconnected to create redundancy, so that if a failure occurred on one segment, data could be sent by another route. But when there are multiple paths in a bridge network, loops can form. In other words, the simple bridge forwarding rules we just discussed can cause a forwarding storm, where the same frames are forwarded endlessly from one network segment across a bridge to another segment. When a bridge receives a frame for which it doesn't have the destination MAC address in its table, it floods the frame out every other port. It also updates its MAC address table with the source MAC address. If the bridge keeps receiving the same frame on different ports, its address table is constantly changing. Broadcast and multicast traffic make this problem even worse. Remember that if the destination MAC address is a broadcast or multicast address, a bridge must always forward it out every other port. When a network has loops, bridges receive broadcast traffic and rebroadcast it out all ports again and again, creating what is known as a broadcast storm. A broadcast storm can block all other network traffic and bring a network to a complete standstill. We don't show it here, but as we saw in the previous scenario, each bridge must also keep updating its MAC address table each time it receives the same frame on a different port. To prevent loops, bridges used the Spanning Tree Protocol, or STP, which selectively disables bridge forwarding on individual ports to ensure that the network topology is loop-free. Discussion of the Spanning Tree Protocol is beyond the scope of this course. Now let's look at the devices used in today's networks. Network devices today look nothing like the repeaters, hubs, and bridges used just a few years ago. Instead of a group of devices sharing the bandwidth of a 10 megabit per second network, network devices today get dedicated bandwidth with speeds from 10 or 100 megabits per second up to 100 gigabits per second. That's an increase in speed of 10,000 times in just a few years. Click the link on screen if you'd like to get a better idea of the relative sizes of network speeds, or click the Continue button to continue with this topic. In this section, we'll see how new devices called switches and routers change networking configurations and dramatically increase network speeds. Let's recall what we learned about collision domains and half-duplex data transmission. As we learned in the last section, bridges break or segment one large network into smaller collision domains. Because fewer devices are competing for network access, overall network performance improves. However, older devices relied on half-duplex data transmission. That is, a device first had to listen before transmitting to ensure that the network was available. The device also assumed there were many other network devices on the same network segment and therefore had to be ready to deal with collisions. In half-duplex Ethernet networks, after a device transmits data, it listens to the network and expects to hear the same data in the exact same pattern. If the device hears a different pattern, it assumes a collision has taken place. If a device must wait its turn to send data, and then cannot send and receive different data at the same time, time is wasted. Waiting and listening takes up valuable network time and makes the network not as efficient as it could be. As we'll see, modern network devices have greatly reduced the chances of collisions, and in doing so, greatly increased network performance. As we mentioned earlier, end-user devices today connect to network devices using twisted pair or fiber optic cables instead of coaxial cables. Twisted pair wiring offered new possibilities for networking that coaxial cable didn't have. When we take a closer look at the twisted pair wires used in an Ethernet environment, we see that there are a pair of wires for transmitting data and a separate pair of wires for receiving data. The pinouts shown on screen are for regular Ethernet end-user devices, such as PCs, servers, printers, and routers, a network device we'll discuss later. Click the link on screen if you'd like to learn more about the wiring for straight-through and crossover Ethernet cables, or click the Continue button to continue with this topic. Because there are two different paths, an Ethernet device is capable of transmitting data onto the network using the transmit pair while it continues to listen using the receive pair. So in theory, Ethernet networks were no longer restricted to half-duplex data transmission, but could transmit and receive simultaneously. In practice, however, it wouldn't work in a bridged network. In a bridged network, a network can be segmented only so far. Users still compete with each other for network access on the same segment or collision domain. As long as that was the case, collisions would still be a problem. It was still necessary to listen to make sure the line was clear before transmitting data, and after sending data, listen again to make sure a collision had not occurred. To overcome that limitation and take full advantage of twisted pair cabling, the switch was developed. Ethernet switches are similar to bridges in that they are both Layer 2 devices that help manage and control traffic. As with a bridge, each port on an Ethernet switch creates a separate collision domain. Just like a bridge, an Ethernet switch forwards traffic and learns which MAC addresses reside off each of its ports. Where they differ is that Ethernet switches have significantly more ports than do bridges. Today, a simple switch might have just a few ports, but an enterprise-level switch can have hundreds of ports. When a single Ethernet switch port can be dedicated to a single end-user device, hubs and bridges are no longer necessary. Because switches dedicate a single bridge port to one end-user device, collision domains have only two devices, the end-user device and the switch. End-user devices no longer compete with each other for network access, and with twisted pair cabling, each transmit pair is an isolated circuit. Because both sides of the connection will receive data from only a single network device, packets will not get corrupted by multiple stations transmitting simultaneously. By isolating each end-user device in its own collision domain and providing two separate paths to transmit data to the switch and receive it from the switch, collisions are effectively eliminated. Without the danger of collisions, devices can freely transmit and receive data at the same time, which is called full duplex data transmission. Full duplex data transmission is similar to using a telephone, where you can talk and listen at the same time. Ethernet switches with full duplex data transmission offer much greater bandwidth than bridges did. With full duplex data transmission and dedicated switch ports, an end-user device can send and receive data simultaneously, effectively doubling network performance. End-user devices no longer have to share 10 megabit per second or 100 megabit per second of bandwidth with other end-user devices. Finally, in addition to basic Ethernet connectivity, switches make possible virtual LANs or VLANs. VLANs provide a way to break a single LAN into separate LANs on the same switch. Earlier we learned that when a bridge receives a frame with a broadcast destination address, it must forward the frame out every other port. The same is true of switches. Segmenting a network with switches fixes the collision problem, but it doesn't address the fact that broadcast traffic must be sent out all other ports, which uses up precious network bandwidth. VLANs help solve this problem. Here you see a single switch with two different VLANs identified by color. Essentially, VLANs are a way to subdivide a LAN. A VLAN is a group of PCs, servers, and other network devices that may be connected to the same switch as other devices, but behave as if they are connected to the same smaller LAN or a completely separate switch. Devices that are in one VLAN do not receive broadcasts from devices in another VLAN. If a device on the purple VLAN sends a broadcast, the switch sends the broadcast out only the ports configured on the purple VLAN. The switch doesn't send the broadcast out the green ports, even though they are on the same physical switch. When devices on different VLANs need to communicate, even if they are on the same switch, a router must be used. We discuss routers in the next section. A more detailed discussion of VLANs is beyond the scope of this course. Switches do have limitations. Because they forward frames just like bridges, they're susceptible to the same sort of network hazards, such as loops, that bridges are. Both switches and bridges must forward broadcast and multicast frames out every port. If there are loops in the network, broadcast and multicast frames can cripple a network. Like bridges, switches also use the Spanning Tree Protocol, or STP, to prevent network loops. Likewise, switched Ethernet networks might not improve performance if a network has a lot of multicast and broadcast traffic. Finally, Ethernet switches might not be able to interconnect geographically dispersed networks. To solve these problems, a different network device called a router is required. Whereas Ethernet switches operate at layer 2 and can examine only the destination layer 2 or MAC address, routers operate at layer 3 and can examine layer 3 addresses. In our next section, we'll examine the difference between layer 2 and layer 3 addresses as well as router operation. Here's a chance to review some of the concepts you learned in this section. As we saw earlier, unicast addresses identify one specific device. Multicast addresses are associated with a group of devices, and the broadcast address goes to all devices. Do you remember how to recognize unicast, multicast, and broadcast MAC addresses? Drag each address below into the correct box. Incorrect matches will bounce back. Earlier in this section, you performed a simple exercise to understand bridge behavior. As you know, switches operate in essentially the same manner as bridges, but have enough ports so that each port can be dedicated to a single device instead of being shared. Here's a similar exercise in which you can apply your knowledge of MAC address tables and switching behavior. Use your knowledge of switch behavior and the MAC address on screen to decide what to do with the frame that has just arrived on port 1. Click one of the 3 buttons to forward the frame on one port or all ports. You will be presented with 4 frames. We've covered many different devices in this section. Here's a chance to see if you can remember the characteristics of each device. Each device below is associated with a characteristic, but only one of the associations is valid. Click the box that correctly identifies a characteristic of the device shown. You have 10 tries. How many correct answers can you identify?